Hello. In this chapter, we are going to discuss first order RL and RC network. Before that, in the beginning, first we will see very brief introduction about capacitor and inductor. We will not discuss physics related stuff here. We will just see its characteristics which are required to analyze a RL and RC network. So first one, capacitor. So if you consider a capacitor with I current and voltage V across it, capacitance C, how we can explain its behavior? So we can write charge stored or accumulated on the plates of capacitor is directly proportional to voltage applied across it. So if we apply a more voltage across the capacitor, then we will see more charge getting stored in the or getting accumulated on the plates of the capacitor. So that itself we can write Q is directly proportional to V, and proportionality constant if you write CV, where C is the capacitance. Okay. Now if I differentiate this with respect to time, so we will get this expression where dq by dt is nothing but current. So I equal to C dV by dt. So this is the relationship between current and voltage of a capacitor. So I equal to C times the dV by dt. So if you want expression for V in terms of I, so I can write like this: dV equal to 1 by C I, or I of t I can write dt, and if you integrate with between the time interval t equal to t0 to t equal to t, then you will get V of t minus V of t0 equal to 1 by C I of t dt. Or if you write V of t, then that will be equal to, sorry, here you have to write t0 and t, then it will be 1 over C integration running from t0 to t I of t dt plus V of t0. So voltage across a capacitor is nothing but a voltage at initial time, or voltage at t equal to 0. Initially what was the voltage across the capacitor, plus 1 over C into integration from t0 to t I of t dt. So this is the expression for voltage across a capacitor. Anyhow, we don't need this equation to solve the problems. We will use the characteristics of a capacitor. So we will see that what are the characteristics of a capacitor. So characteristics of capacitor. How you can explain the behavior of a capacitor? So first one is, there is no current through capacitor if the voltage across it is not changing with time. So this is the first one, no current flows through, no current flows through capacitor if voltage across it is not changing. If voltage across it is not changing, with time. So in a way we can tell the capacitor acts like an open circuit. Capacitor acts like an open circuit for DC. DC means you are not changing the current with time. You are not changing the voltage with time. So in that case, DC voltage if you apply, capacitor act like an open circuit. No current flows through the circuit. So that is indicated by an open circuit. Second one, this is very important. We are going to use this characteristic in the problem solving. So a capacitor resists abrupt change in voltage across it. For it needs an infinite current. So if a capacitor is having a voltage V0 at a particular instant of time, so you want to change that instantaneously, then you have to apply an infinitely large current, which is not possible. So what I mean, first consider a resistor. If it is carrying a voltage 5 volt at t equal to certain instant of time, let it be t equal to 0, you would like to change its value from 5 volt to 6 volt. So you will remove 5 volt battery and apply 6 volt battery. So as suddenly what happens, instantaneously the voltage across resistor will change. It will not resist any change in the voltage. But if you consider a capacitor, initially it was 5 volt, suddenly you change the battery to 6 volt, it will not change instantaneously. It will take certain amount of time. Ideally speaking, it takes infinite amount of time to reach from 5 volt to 6 volt. But in practical cases, we will see that later, after 5 time constant, it will reach the maximum value. Okay, so we will discuss that later. So finally, a capacitor resists abrupt change in voltage across it. This concept will be clear when we solve many problems. There we will see how capacitor resists change in the voltage. Third one, an ideal capacitor. An ideal capacitor does not dissipate energy but stores only stores it. So that means if you take a resistor, it will dissipate in the form of heat. It will dissipate the energy in the form of heat. But if you consider an ideal capacitor, it will not dissipate, it will store the energy. However, in practical cases, it will have series resistance and it will dissipate energy. So you cannot store the charge permanently there. Okay, so that will be discharged, and in practical case it will dissipate. Okay, so that is about the characteristic. Now using this, we will define initial condition with respect to capacitor. Initial condition. So initial condition here, suppose if you consider a capacitor with voltage 0 at t equal to 0, a particular instant of time, no voltage is there across the capacitor. Now at t you want to change the condition of the circuit, you want to change the voltage across it, and I will do that action at t equal to 0. So soon after that, that is t equal to 0 plus. So we will define this instant of time, that is called t equal to 0 plus. What do you mean by t equal to 0 plus? It is the soon after t equal to 0. It's a very, very tiny time interval. Soon after t equal to 0, what you get is 0 plus. Similarly, we can define t equal to 0 minus, just before the t equal to 0 moment, that is 0 minus. So we will consider only t equal to 0 plus here. So t equal to 0 plus means it is the moment just soon after t equal to 0, that moment, that instant of time, what will happen? The capacitor voltage will not change because it resists abrupt change. How to represent now? This voltage, initial voltage is 0, so it will continue. The voltage equal to 0 continues. How to represent that 0 voltage? It can be represented as a short circuit. Short circuit. So here short circuit represents no change in the voltage, or 0 voltage across the capacitor. So that is represented as like something like short circuit. Okay. So here short circuit indicates 0 voltage across capacitor. Suppose if you consider a capacitor with V equal to V naught, not 0 volt, V naught volt. So that time at t equal to 0 we are considering here, and you want to change the behavior of the circuit. Soon after that, if you want to see the voltage, it will not change. It will not change the voltage across that. So here also it retained the voltage at t equal to 0. Same voltage it is retaining. Here also it will retain the same voltage. What is that voltage? V naught. So it can be modeled as a voltage source with V naught value. This also I can write in the same way, because it can be represented as a voltage source. This one can be represented as a voltage source with V equal to 0, because initially there were no voltage across the capacitor. Same condition prevails. So V equal to 0. That is nothing but a short circuit. But here we have a voltage V naught. So at t equal to 0 plus, it can be modeled as a DC voltage source at V equal to V naught. This is only at a moment t equal to 0 plus. However, as time passes, it condition changes. Okay. So the voltage across the capacitor changes, but I am talking only soon after t equal to 0. Okay. Now, similarly, we can write final condition or steady state. We can write steady state. Steady state. Steady state means you apply a DC voltage across a capacitor and do not change anything, keep it as it is, do not change any voltage. It's called steady state. Capacitor will attain a steady state. In that steady state, how capacitor can be modeled, that we have already discussed here. See this one characteristic. No current flows through the capacitor if voltage across it is not changing with time. You are keeping a constant voltage across a capacitor. What happens? No current flows. So I have to represent model like that. So if consider a capacitor and you have applied a DC voltage, you are not changing with time. How you can model it? You can model it as something in which no current is flowing. How we can represent? Nothing but a open circuit. So you can represent it as open circuit. At t equal to infinity means after long time you are not changing any voltage across the capacitor. It will behave like an open circuit. No current will be flowing. You want to make current flow through this one, you have to change the voltage. That also at soon instantaneously you cannot change. You need some time, then only it will change. Okay. So this is about the capacitor.